There. Okay, so our speaker today is Georg Tamme from the University of Mainz, and his talk is about K-theory and regularity. Please, Georg, go ahead.
Yeah, thank you very much for the invitation. It's a pleasure to give this talk here. So yeah, so the title is K-theory and regularity, and I mean somehow the original things I will say is this is all joint work with Moritz Kerz and Florian Strunk. But somehow I want to start with some with an introduction to these kind of problems. So maybe this is well known to the experts. So let me start with this very classical theorem of let's say of Serre and Quillen, namely that if you have a regular Noetherian ring, so if A is regular Noetherian. So by the way, is it big enough? Is it readable?
I can read it, but it's small, but I can read it.
Yeah, I mean, this also depends on the size of your screen, I guess.
Yeah.
So
mine is small, but maybe if I were, Gisela, are you following it on an iPad?
Yes, I can read it.
Oh, you can read it? Okay. Yeah, so.
And so feel free to interrupt with any questions.
Mm-hmm.
So this classical theorem is if you have a regular Noetherian ring, then its K-theory is somehow homotopy invariant with respect to polynomials. So then Ki, the canonical map from Ki of A to Ki of A, and then join one polynomial variable. This is always an isomorphism for all I bigger than or equal to 0. So I think so here some of the case I equal to 0 I think is basically due to Serre, and the case of positive I is due to Quillen, and the proof is in principle similar once you have Quillen's machinery somehow for the higher K groups. And let me also say that so this I feel a bit uncomfortable because this is a non-commutative geometry seminar. So this theorem is really also true in the non-commutative setting when you interpret regular as saying that every let's say we work with the right modules all the time, and then the ring has to be a right Noetherian, and every finitely generated right module has to have a finite resolution by finite projective modules. This is the definition of regular in the non-commutative setting, I would say. And in the commutative case, it's the same as the classical definition that you learn in commutative algebra via local rings and the number of generators of all the maximal ideals. Yeah, so that's one thing, and the other thing that is also known is basically due to Bus. I think that when in the same under the same assumptions, the negative K groups vanish. So this is 0 for all negative I. So in particular, the first. So because if A is regular, then also AT is regular. So you see that this here holds in fact for all I, simply because everything vanishes in negative degrees. Okay, so now of course you can ask, is there any is there a converse to this? So can you hope that whenever you have a ring such that you have these isomorphisms, will it be regular? And I mean, in this generality, maybe this doesn't really make sense. But so okay, so let me first say that from now on, everything is commutative in my talk. So I mean, all the rings are commutative, although there will be some non-commutative techniques, at least behind the scenes. Okay. So to formulate a more precise converse, let me first recall the following definition. So let's fix some integer n, and then we say that a ring A is Kn regular. By definition, if and only if it has this homotopy invariance property for the functor Kn. So if and only if Kn of A, the canonical map to Kn of A, and then there's one thing, it's not sufficient to join one variable, but you have to look at the finite number. So let's say T1 to Tr, if this is an isomorphism for all R. Okay, so that's a definition. And let's look at some examples. So the first example is, of course, follows immediately from this theorem before. So if A is regular in the above sense, regular, say, Noetherian, then it follows that it's also Kn regular for all n. So A is Kn regular for all n. Yeah, so the only little point is that if A is regular, then AT is also regular. So you can apply this homotopy invariance twice. So you see that you get any finite number of variables here. Okay, that's the first example. But there are somehow also very non-Noetherian examples of Kn regular rings. So which are Kn regular for all n. Namely, let me cite the following. So if A is a commutative C-star algebra, then it's also Kn regular for all n. And this is a theorem of, I mean, I think it was conjectured, and maybe also kind of proved by Rosenberg, and then by Willy Cortiñas and Andreas Thom. And in fact, they prove a bit more. Namely, you can also look at something like you take a commutative C-star algebra and then tensor over C with the regular C algebra of finite type, something like this. Maybe it's even true if you look at something which is smoothed over a C-star algebra. I don't know if you have thought about this, but let's see. This is at least true in the next example, which is it is quite recent. So if A is a perfect, yeah.
One thing that I would point out that in the second example, the negative K theory is non-zero.
Yeah, thanks. I also wanted to point this out, but I forgot. So thanks, yeah. But usually have K, let's say K minus I non-vanishing. So I hope you, yeah. So there can be non-vanishing K theory in negative degrees. Yes.
There is some question in the chat.
Oh, I don't see the chat.
Do you expect the second exp for the non-commutative cases?
Maybe that's a good question, and I have no idea. And maybe
Rosenberg conjectured that every sister algebra is K0 regular.
Oh.
I mean, there are other very non-commutative sister algebras, namely those who are stable, that are also K regular, Kn regular for all n. But I don't know of any sister algebra that is not Kn regular for all n, so I don't know. At least there should be K0 regular.
Yeah, okay, thank you. And so the other example I wanted to give also in the commutative cases, if you look at perfect FP algebras, then you have the same conclusion. So it's also Kn regular for all n. And in general, so usually it also has negative, or at least negative K theory can appear. And so let me just recall what this means. So perfect, this means that the, so i.e., because this will show up later on, that the Frobenius so sending X to the P power map, this is an ISO. That's the definition of a perfect FP algebra. Ah, yeah, and this, let me also give the reference here. This was recently proven by Ben Antio, Akin Matthew, and Matthew Morrow. This was on the archive recently. It's a paper called The K-Theory of Perfectoid Rings, where they, amongst other things, prove this. Okay, so you see there are some classes of examples which are Kn regular for all n, and we are mainly interested now somehow in a converse in this to this first one here. So in the Noetherian case. Okay. So let me first of all give some. So let me try to give you some feeling what this Kn regularity means. So maybe this is a remark. Okay, let's first of all look at the case that A is K not regular. So what does it mean? I mean, I cannot answer this question completely, but at least you see that if it is K not regular, then in particular it's also pig regular, where pig regular just has the same definition, but you replace the functor Kn with the Picard group. This is simply because you have a surjective map from K naught to the Picard group given by the determinant. And you see that somehow that this map here is an isomorphism really just means it's surjective, because it's always injective because it has a splitting. And yeah, so if it's an isomorphism for K naught, and because you have this surjective map, which is of course natural, you see that it will also be pig regular. And this is in fact something which you can really understand. So this is really some kind of regularity condition. Namely, this was proven by Traverso's theorem, that this is equivalent to the reduced string of A reduced, being what is called semi-normal. Sorry. So first of all, you need to look at the reduced string here, because somehow K naught can of course not see the difference between A and its reduced string, because it's nil invariant. And semi-normal means, so this is a bit weaker than being normal. So the precise, I mean, this doesn't play any role here, but the definition is if you have two elements in your ring which satisfy x squared is y cubed, then there must exist an element S such that x is s cubed and y is equal to s squared. So it's a weird definition, but it's something in the direction of regularity. Okay, so that's the first thing, and the second one is K1 regularity. That's in fact a bit easier. So let's assume that A is K1 regular. Then again, because so I'm using here really that we are in the commutative situation, then the units are always direct summand of K1. So by a similar argument, we see that the units are polynomial homotopy invariant. So in particular, we see that A is reduced. So they can be reduced, meaning there are no non-trivial nilpotent elements. So in particular, we see, can now observe that, I mean, being reduced is also some kind of regularity. In fact, if you look at zero-dimensional Noetherian rings, so if A is a zero-dimensional Noetherian and K1 regular, so meaning reduced, or implying reduced, then we see that's that A is in fact, I mean, so it's an Artinian ring which is reduced, so it's just a finite product of fields. Okay, so in this case, A is in fact regular. Okay, so this was easy. This is somehow the first converse statement one can prove, and then the next step somehow this was done by Vorst. So that's the main theorem of Vorst. So he proved them as the same, the analog statement for one-dimensional rings. So if A is one-dimensional Noetherian, and now K2 regular, then it follows that A is, sorry, and this is not what he proved, in fact. There's one additional assumption, namely A has to be essentially a finite type over a field. That's important in his proof. But then he proves that A is regular. And if I remember correctly, then this is basically, I mean, somehow, so you understand quite well what kind of singularities could appear for curves over a field. And then using this, somehow you can deduce the regularity given K2 regularity. Okay. So this is what was proved, and then he. Wait, question?
Yeah, will you mention that Kn regular implies Kn minus 1 regular?
Yeah, I will do this later. So then he conjectured that, I think I will even prove this if I have enough time, because that's a nice argument. So then he conjectured that if A is essentially a finite type over a field, so same assumptions, and its dimension of A plus 1. Sorry, this should be, this should be an index. So if it's K dimension plus A, dimension of A plus 1 regular, then A is regular. So this is Vorst's conjecture, which generalizes the example. I mean, these remarks 2 and 3 somehow. Okay, so that's the conjecture, and this is I want to say something about in the positive characteristic case. So, but first of all, let me say what is known in characteristic 0. So this is proven completely in characteristic 0. So meaning if your ring is essentially a finite type over some field of characteristic 0. So this was also by Willi, Cortiñas, Haesemeyer, and Weibel. And so they even prove a final result. Namely that if your ring is KD regular, then the singularities are in codimension at least D. So if in particular, if it's dimension plus 1 regular, then the singularities are in codimension at least dimension plus 1, so it's empty. So there are no singularities. And then there was somehow, at least partially, so if A is a finite type, so not a so essentially a finite type means it's a localization of something of finite type. So if it's a finite type over a field, type over a field of positive characteristic, and this field should be perfect. Let's say of a characteristic P, and you assume resolution of singularities, assuming resolution of singularities, then this is then it's also proven in a paper by Geisser and Hesselholt. Okay, and somehow, so now I want to formulate what we prove, and so some of the I mean, there are, of course, these two proofs, there's something, of course, similar so some techniques are, of course, similar in both proofs, but they are also a bit different. And our proof is more like this Geisser-Hesselholt approach. And I will try to outline how this proof goes. But first I have to, so to formulate our result, I have to introduce a bit more notation, so characteristic P case. Namely, we cannot prove this with this form of Vorst conjecture. We cannot prove in full generality, because so the problem is comes somehow from imperfect fields, and somehow we have to. So we have a weaker bound. I mean, somehow we have to replace this dimension here by something which we call the P dimension, which is bigger usually. So let me define the following. So first of all, if F is a field of characteristic P, positive, then we define the P dimension of F. It's also called the P rank sometimes. That's simply the dimension over F of the module of absolute Kähler differentials. So omega 1 of F over Fp, or you get over Z and so on, it's all the same. So if you would do the analog definition here in characteristic 0, this would just be the transcendence degree of your field over Q, when you put Q here. But in characteristic P, it's not the transcendence degree, because, for example, so a field F is perfect if and only if its P dimension is 0. Okay, this is because, yeah, I mean, basically the point is that whenever, I mean, if it's perfect, recall this means that the Frobenius is an isomorphism. So every element is a pth power. And if you look at its differential, that's P, I mean, d of x to the P is P times something, so it's 0. So the differential forms vanish. And you can also prove the converse, it's not so hard.
Sorry, but if F has descendance degree, I don't know, 1, then doesn't, I mean, this dimension is not 0, or is it? Even if it's perfect, because it's too big, right? Doesn't it? I mean, no. You could have something like you could look at something of Fp and then round brackets T. So yeah, this is purely transcendental, but this is not perfect. So this is transcendence degree 1, and this dimension. That's not perfect. Yeah.
But then if you go to a perfect closure, so then you adjoin again all pth roots of this element T also, all p power roots of T, and then it becomes, this dimension here becomes 0 then.
Okay. So it's like perfection implies non-ramification, something like this. That the omega 1 is 0.
Yeah, maybe you can interpret it as something like this.
Okay. It's the dimension over X.
Yeah. It's so by the way, so yeah, whenever you have a perfect FP algebra, it's always formally étale. Even so, it's formally unramified, and it's even formally étale.
Okay.
yeah, so this is a definition for fields, and then using this we can somehow modify the usual definition of Kull dimension in the following way. So if let's say X is an FP scheme, I use schemes now because then it's easier to write the definition, but I'm mainly interested in affine schemes after all. So then the P dimension of X is by definition the supremum of the following things. So we look at the Kull dimension of all local rings. So this would just be the usual dimension of the scheme, the supremum of all dimensions of the local rings. But then we add the P dimension of the residue field. So let's write kappa of X for the residue field at the point X. So and here X is in X. And it turns out that this okay, it's just a definition, but this has somehow good formal properties for a dimension function on FP schemes or commutative rings in characteristic P. So let me just maybe again to give you some feeling how this behaves, just 2 facts. So or 1 fact. So if A is a finite type, over a field, then it follows that this P dimension of A is simply the usual dimension of A plus the P dimension of the base field. So in particular, if it's finite type over a perfect field, it's just the usual Kull dimension. But if it's over something non-perfect, then you add the P dimension of the base field. And similarly, if A is complete, let's say complete local Noetherian with the residue field, little k, then you have the same, okay, let me write it like this, oops. Then you have the same conclusion. Then it's also just the usual dimension of A plus the P dimension of the residue field this time. Okay, and now with this I can formulate the main theorem. So let's call this theorem A, and this is, as I said, with Moritz, Kerz, Florian, Strunk, and myself. So there are some technical assumptions. Let's say A is excellent, Noetherian, and we need one more assumption, namely that all the residue fields, okay, kappa X over have somehow finite P dimensions. So this, okay, this is not completely clear from the definition I gave you, but so I asked that for all points in the spectrum of A, for all prime ideals, if I look at the residue field, there should be finite over its subfield of Pth powers. And so this is that's the assumption. Then if A is K P dimension plus 1 regular, then A is regular. Okay, so that's the theorem, and so you see in particular it's I mean it's something, but it's not precisely what was conjectured. I mean not even and also sorry I forgot somewhere the Noetherian FP algebra, of course. So it doesn't have to be essentially a finite type or something over a field of characteristic fields. It's just over something over FP, which is Noetherian, and yeah, in this excellence condition. Okay, so in particular, you get this as a corollary if we look at the case of a perfect base field and something really of finite type. then we know that the p dimension is just the dimension. Then in this situation, it's the Vorst conjecture. So so somehow in particular you get let's say this Geisser-Hesselholt result. But without assuming a resolution of singularities. Okay. Okay, so that's the theorem, and now in the remaining time, I want to try to indicate a bit how the proof goes. So what the fundamental input is, and I want to start with some elementary observations about this notion of Kn regularity. So that really already indicated before. So okay. So what you see here, I mean, regularity, for a ring to be regular, this is a local condition. So it's regular if and only if all the local rings are regular. And whereas for this thing here, it's not so clear that this is a local condition. And in fact, this was a lemma, one of the results by Vorst also. So if A is Kn regular, then any localization of A is also Kn regular. So let me put it like this. So S inverse of A, so this means localization of A at some multiplicative set S as also Kn regular. So you see in particular, we have that all the local rings AX are regular, Kn regular. For all X in the spectrum of A. So in particular, this allows you later on to reduce to the case of regular local rings, of regular rings. And so let me briefly give you the proof, because it's easy nowadays. And it shows a bit how to work with this notion of Kn regularity. So that's a nice trick. So let's assume, I mean, this is just for simplicity of notation, basically, that S, this multiplicative set, is given by the powers of one element F. So we just invert one element F, and then we do the following. So we look at our ring. Okay, so we know that A is Kn regular, and we want to prove that this localization, which I write A index F, this is by definition then S inverse of A. We want to prove that this is also Kn regular. So we look at this map here this time. So instead of looking at the map from A to the polynomial ring, you can of course also look at the splitting map, which sends T to 0. And this is of course AF. And so being Kn regular means that this map here induces an isomorphism on Kn, when you also allow more than one variable here. But let's do it just for one variable. And then you form the following Milnor square. So this will be a Milnor square. So we have this map here is surjective, and we look at the pullback somehow of the square, which is then given by the following ring. So these are polynomials in AF whose constant term is already in A. Yeah, so this is a pullback square, and now you observe that this map here, this is flat. And in general, if you have a Milnor square, you don't get a long exact sequence of K groups in positive degrees. But in this case, because this is flat, you get this long exact sequence. And so then you get, let me write it like this. So this gives a long exact sequence, or if you like, a pullback square of K-theory spectra, just to make things a bit easier to formulate. AT to K of A. K of AF T to K of AF. So now we want to prove that this map here is an isomorphism or is an equivalence, and so this is also a Pullback square. So that this is a Pullback square, or homotopy Pullback square, essentially just means that you have these long exact sequences of homotopy of K groups. But now you observe that this thing here, in the upper left corner, this you can rewrite, namely, this is the same as the direct limit of the K theory of AT, where the transition maps just send T to F times T. So you multiply the variable by F all the time, and then you see in the direct limit, in the constant term, you always just have A, but in the non-constant terms, you can have denominators. And so this is, first of all, without the K, you have this direct limit description of the ring. And because K theory commutes with direct limits, you get this also for the Ks. And then you see somehow in each, this map now I claim is an isomorphism just because A was assumed to be Kn regular. Sorry. So at least in, okay, maybe I'm, yeah, so anyway, yeah, maybe I'm cheating a bit here. So this is an isomorphism in degrees n, and then I claim that this also follows for the lower one. I think you need that you also have splittings here. But anyway, so this implies that also the lower map is an iso in degree n. Okay, so the main trick is somehow that you write this thing here as the direct limit of AT itself, with this multiplication by F map.
One question.
Yes.
I mean, this ring also appears in Vorst's original paper, but the fact that you get a pullback square, I think in that situation invoked some localization theorem of Karoubi, I think.
Yeah.
So when you said nowadays, one can prove this this way, I suppose that to conclude that this Milnor square gives you a homotopy pullback, you are using your circle thing.
Yeah.
Okay.
I mean, of course, I like these Milnor squares. But you're right. I mean, you can also. So this was also proven. I mean, the precisely same result was proven by Thomas and Turbo. It's in fact an exercise in Thomas and Turbo to prove this using his localization theorem. And Vorst didn't have this, so he only had these localization theorems where something has to be a non-zero divisor or something like this. It was more complicated at that time. So this I was referring to. It's already since Thomas and Turbo, so since 30 years or so, that it's easier to prove. Yeah. Okay. So I hope I just realized that I didn't check the details here, but I hope it's something like this should be correct. Okay, so we see that somehow Kn regularity is preserved under localization, and this is something which is really only true for in the affine case. You could also define Kn regularity for this notion. You could define for schemes also. But for schemes, it's not true that if you have a Kn regular scheme, then it's not true that every open subscheme has to be Kn regular. That's precisely the point why you need this affineness assumption in Vorst's conjecture. So it's definitely false. There's also a counterexample in the paper by Willi and Haesemeyer and Weibel that if you have something global, so non-affine, then the Vorst conjecture is false. And this is the lemma somehow that breaks down. Okay, and now I can finally mention this corollary that Willy also mentioned before. So if A is Kn regular, then it follows that A is also Kn minus 1 regular. Yeah, simply because Kn minus 1 by the fundamental theorem is a direct summand in Kn of A, and then adjoin T and T inverse. And then somehow if A is Kn regular, then of course also the polynomial ring is Kn regular, just by definition, that's clear. And now you can localize one element, and it's still Kn regular by the previous lemma. And so you see that because this is a direct summand, this then also, if you adjoin more polynomial variables here and here, then it's still an isomorphism.
Yeah, just one thing I'd like to mention, that in this corollary, A need not be commutative, and neither in the lemma.
So it's associative. So it's not necessarily commutative. Yeah, that's right. And the same proof works, I guess. Okay, so we have this, and then from this we deduce another corollary, which is somehow the key input in all these proofs. Namely, you compare K-theory to homotopy K-theory, to Weibel's homotopy K-theory. So, so if A is Kn regular, then it follows that the canonical map from the K-theory of A to the homotopy K-theory, this is an iso in degrees less or equal to n, and it's surjective 1 degree higher, surjective in degree n plus 1. Yeah. So I don't know, is this homotopy K-theory something known, or should I say something about this?
I know. I mean, I don't know.
I can just.
My people in my group should know about this. Yeah,
okay.
But it's not the only public that you have.
So this is by definition. You look at the K-theories. So K-theory always, by the way, means a non-connective K-theory, and then you look at A adjoin somehow. Okay, let me write it like this. T0. So you look at this algebraic version of the standard simplex TP mod out by sum of the Ti equals 1. Now, if you vary P, this is a simplicial ring, and you can look at the K-theory. So this is a simplicial diagram. Now you apply K to it, so you get a simplicial spectrum. I mean, at that point, you really have to work with spectra. I mean, you can avoid it, but it's but yeah. And then you take the geometric realization, and now you use that. So these rings here are all. I mean, you mod out by something, but these are just polynomial rings again so of somehow degree p, and because you know somehow the K-theory in degree the homotopy K-theory in degree n only depends on the K-theories of these rings in degree less than or equal to p to n, and somehow from this you can deduce this isomorphism in a range of degrees. Okay, so that's one input, and now I have just 5 minutes, so let me try to say how you prove this theorem now. So to prove theorem A, this kind of weak version of Vorst's conjecture, you combine. So that's somehow the strategy is this Kaiser-Hasselhoff strategy. So you always combine a vanishing theorem for homotopy K-theory for KH with a non-vanishing theorem or let's say non-vanishing, it's really a non-vanishing lemma for K-theory. So let me maybe, okay, let me formulate first the vanishing result, and this is really the where the hard work goes into. I mean, this is somehow also where our new contributions are, I think. So if X is an Ethereum FP scheme, then the homotopy K theory, KHI of X. So now we look at the homotopy K theory with Z mod P coefficients, and then this vanishes above the P dimension. So for I bigger than the P dimension. Yeah, so that's the vanishing result, and you see if you combine this with this theorem here up to these mod P coefficients, you see if your ring is Kn regular, then because K theory in these degrees is isomorphic to KH theory, to homotopy K theory, you also see that the K theory vanishes in these degrees. And then we have we also have a non-vanishing. Yeah, let me maybe first state this non-vanishing lemma, and then I can say something more about the theorem if I still have time. So that's already essentially due to Geisser and Hesselholt. So if how do I formulate this? Let's say if K is a field of characteristic P, so this will be somehow one of the residue fields of our ring, and we look at the following ring B. So this is just K adjoined X1 to XR divided by the square of the maximal ideal of the ideal defining 0. Then you can always find a symbol somehow in K theory which is non-zero. So and we let moreover, let's say Y1 to YS elements in the base field K, which are P independent. So there's the notion of P basis. In the definition before for P dimension of a field, this essentially means that differentials of these Ys are linearly independent. And then it follows that if you look at the following symbol, this does not vanish. So you take, that's anyway invertible. If we take these elements, and then we can also have these units, 1 plus x1. And so these are all units. And this gives us a symbol in, let's say, the K theory in degree R plus S of this ring B with Z mod P coefficients. This is non-zero, and this follows, this you can check. So for the proof, you simply use the Dennis trace map to Hochschild homology and check it there. So check in Hochschild homology of B over FP. And how do you use this now? So the point is in the proof of the theorem, you can reduce to the local case, this I said before, and then you can even reduce to the case of a complete local ring. Now you have a complete local ring, and it follows from these structure theorems that if this has this embedding dimension R, so if the maximal ideal is generated by R elements, then you get a surjection from this local ring to this ring here. And because you can lift, this is a symbol, so you can lift it to your local ring. And then you see the K theory of this local ring does not vanish up to the embedding dimension plus this P dimension. This comes from these elements from the base field. And on the other hand, from this result, you see that the K theory, if you have K blah 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 regularity, the K theory must vanish in this high degree. And if you combine these two things, you get that this embedding dimension has to be less than or equal to the dimension of the ring. And this is the classical definition of regularity in commutative algebra. Okay, so I think my time is over, so let me stop here.
Okay, thank you very much. So I have two competing. So let me see what is in the chat. The Varshi asks, to what extent do these results carry over to the rigid analytic setting? That is, if your A is, say, an affinoid algebra, are there similar regularity results?
That's a good question. And so first of all, so if you have a regular affinoid algebra, then of course the K theory is still somehow polynomial homotopy invariant, but that's maybe not what you are really interested in. So you are maybe asking if you somehow instead of polynomials, you look at power series of this usual rigid analytic unit disk, and if you have a regular K algebras, so K is now, let's say, a non-Archimedean field, and you look at the algebraic K theory, if you look at p-adic completion of polynomial rings, this would correspond to some things which converge on the disk. Yes. Yes, thanks. On the closed disk, and I mean, for these, if you just have a polynomial ring and p-adically complete, then it's also homotopy invariant, I think, for this special kind of ring. But in general, it's not. So if you have something, if you have some regular affinoid algebra, and you look at this, when you take polynomials over this and p-adically complete, then this will in general not be the algebraic case will not be invariant for this. And the problem is that so I think I should know this better, but I just forgot the details. At least you need something like good reduction. So if your thing has a model which is, for example, if you have your non-Archimedean field, and this is has the ring of integers. If you have something which is smooth over the ring of integers, and your thing comes as the p-adic completion of this smooth thing, then there's a chance that the K theory is invariant with respect to this somehow p-adic unit disk. Yeah. Okay. But I'm not sure if you really know this. I think we know it for K naught. It's yeah. Sorry.
Okay, so there are two people with raised hands. So let Rabeya Basu ask first.
Hello, I'm Rabeya. Yeah. So I think this the last lemma which you have written here, it is a similar lemma which Vorst has used in his paper in his proof. For the K1 triviality of the polynomial ring for a regular.
I don't know if I got this correctly. Are you talking about
see, one of the result of Vorst is saying that if A is if the original ring is regular, excellent, Haesemeyer, etc., then SLN Rx is same as EN Rx. So in that paper, Vorst used as I remember that this similar type of result, and that this type of lemma was the main ingredient. So my question is that do you think that under certain condition we can expect that Vorst result is okay for more than one variable? The K1 level.
So which result of Vorst do you mean?
I am looking at the paper right now. So
you mean the Vorst's original paper for?
Yeah, Vorst written a paper that SLNRX is ENRX.
You are talking about some special linear group and
Yes,
elementary.
yes.
Oh, I see.
So I think this, here also used this similar type of lemma, not exactly, but the similar concept is independent variable is also there. So, and that is the main invariant. So by my question is that under what condition we can expect Vorst, that result is true for more than one variable?
Oh, yeah. This I think I don't know. I don't know this result of Vorst so well. I've heard about it, but I never I've never used it or looked into it, so I don't know.
Yeah, I think okay. Sorry, I thought that this work is very much related to that paper. That's why also.
Yeah, no, I think it's a different paper where he does these things about.
Yes, different paper, but related. So.
Yeah, it could be. I have to look into it. Right now, I cannot say. Maybe there's maybe we can use something, but I don't know.
Okay. Thank you.
okay, so Thomas Hüttemann is next.
Yeah, thank you. Many thanks for this beautiful talk. I enjoyed that a lot. So I have two questions. One is a non-mathematical one, namely, would you be willing to share your notes, what you wrote?
Yeah.
Okay, that would be great. The second one is mathematical. It's maybe not really a question, so it's not a very well-defined question in any case. Would it make sense in this context of KN regularity and also your results, instead of focusing on inclusion of a ring into a polynomial ring, to look at inclusion of a ring into any n-graded ring, which contains the given one as the degree 0 subring? I mean, under suitable flatness assumptions also, it wouldn't make any difference, because then Quillen already showed that the graded ring will have just the K-theory of the degree 0 subring. Right, so I don't know if that makes any sense, to be honest, or if one gets anything different.
Yeah, I mean, so I think we know that at least KH theory is also invariant for these for any graded rings, right?
Homotopy invariance implies that invariance.
Yes, but if you have a regular ring, then it's maybe not clear that it's also is, or is it? I mean,
well, so along these lines, there's the conjecture of what's his name? Well, that we proved about semi-normal monoids. So if you have the monoid ring over a regular ring, sorry?
Gubelace?
Gubelace, exactly. You have a monoid ring over a regular ring, and you suppose some assumptions on the monoid, such as having no units and several other assumptions. Then the K-theory, yeah, well, the K-theory, if it's regular, then the K-theory, so it's, yeah, that there is a kind of Frobenius that acts nilpotently on it. So let me, so since I cannot, it's a shame that I cannot be coherent even talking about my own results. So, but let me find it and I will tell you. But this is a kind of graded homotopy invariance result.
So there you look at something like you
need to invert all dilations. That's
yeah. Yeah.
To get homotopy invariance.
Yeah. So if A naught is Kn regular, can we say if that a Kn a graded ring is also Kn regular? I guess not in this generality. Because
Yeah,
I mean,
it can't be expected, I assume, in full generality, but maybe one can have relatively mild assumptions on the ring or the graded ring. I don't know. As I say, one needs to be careful if one goes back into the context where K-theory doesn't see a difference anyway, then of course that becomes a pretty obvious statement.
Yeah. Yeah, maybe, yeah. So I have not thought about this so much. So, but maybe you can say something.
Yeah. Okay. Well, thanks.
Okay. So I have two questions. One, the trivial question is, if you have theorem A, then maybe there was a theorem B.
No.
Okay. Maybe you wanted to say it to get to theorem B, and you couldn't because of
yeah,
time.
thanks. Thanks for asking. No, I just wrote theorem, but then I wanted to refer to this at this point. So this is why I wrote theorem A.
Okay. And another more philosophical question: is there a setting such, so say DG categories, right? So you can formulate a notion of regularity for such things, and maybe, and I'm not sure about the dimension thing, but yeah, but and the serianity too, some finiteness condition. So is there any hope of having any format, maybe by a DG category? So if you can prove that K regularity for DG category implies regularity, then you could apply this to the perfect complexes on a non-commutative ring, and then obtain a version of this result in the non-commutative case. So
yeah, that's a good question. I mean, so first of all, I think you can make sense of somehow regular. I mean, if you have some DG categories, then you can. I mean, there's a notion of regularity. I think. I mean, you can say something like there exists a bounded T structure or something with. Somehow you have something like there exists a bounded T structure on the big category which restricts to perfect objects or something like this. So somewhat simply generalizing this Serre's characterization of regular local rings, so this I think you can make sense of. But then, and I think it's also true that if you define this correctly, which I cannot do right now, then that you can prove that the K theory is homotopy invariant or polynomial homotopy invariant in this setting. But then how to deduce a converse, I'm not so sure. I mean, these techniques here. So, for instance, what goes into this vanishing theorem here, this is really somehow heavily commutative at the moment. I mean, this uses, so the basic idea is that we know that this here satisfies CDH descent, and then CDH locally somehow we understand more or less. So you can reduce to the case of valuation rings, and so feels like smooth, but this does not really work. But you can reduce to valuation rings, and in this case, you can prove that these things So this is again K-theory for evaluation ring, and that has to do something with differential forms. But somehow this step I have no idea what to do in the non-commutative setting.
But I mean, so there are these standard tricks that you can do, that you take, say, your DC category and consider for any scheme X, you consider, so the DC category is called A, and then you do A tensor perf X, X being the scheme.
Yes.
Right, and now you take the K theory of that. So that's a functor defined on schemes. And then if you have some theorem about sheaves of spectra, say, on your favorite category of schemes, and then you apply it to this, then sometimes you get results about the K theory of the DC category you were interested in. I mean, there are some arguments that you can do, as we do in this paper on the Goubelat's conjecture. That
okay. So it's, I mean, if you already, so your DG category that you start with already has some good properties, or you mean you can deduce something about the DG category?
So let me wait. No, this. Yeah, so here, so this is yeah, you have, so this is a regularity result. You have a submonoid of a torsion-free abelian group that has no non-trivial units, and yeah, so you can invert dilations in K theory. This is what this limit is, and then you want to prove that this is a K theory, that this is invariant under adding this, taking this monoid ring once you invert dilations, right? And so the coefficient ring, you see, can be an associative ring, that blah blah blah, an associative ring. So all these are non-commutative versions.
Yeah.
And the way you get this is along the lines of what I was telling you about just a minute ago. So let me see how I get this back. There are these DC categories falling around. So let me see. Yeah, here, you see, here is, yeah. So the theorems along this line, that you have a pro-sheaf of spectra that satisfies certain assumptions, then it satisfies CDH descent.
Yes.
Then the pre-sheaf of spectra just needs to satisfy these properties, and then you can apply it to things of the form you take your ring A, and you tensor it with perf.
Yeah.
And this is the functor where you apply your result to. So that way you can obtain results for non-commutative rings. So maybe, I mean.
But I think this is, I mean, for example, you could probably prove, which is then not new, that if you have, and you can prove that something is homotopy invariant But for the converse, I think it's, yeah, maybe, okay. Yeah, okay, I see. Maybe one can say something. Yeah, that's a good point. I have to think about this. I don't know.
Mhm, mhm.
I mean, but yeah, okay. I mean, this, so you, okay, you could try to prove somehow a version of this vanishing theorem for where you have the more general situation that you have something which is, I mean, some DG algebra. So,
Mhm.
I mean, you tensor somehow this, that there was a scheme X, and if you take instead of X, you look at K-theory of perf X tensor with your DG algebra or DG category. Yeah, maybe one can prove something about these. And then,
Yeah, the non-vanishing part is the trickiest, I suppose. Yeah, because these symbols, yeah, you should have to do that by hand in each example, I suppose.
Yeah, I don't know.
Okay, so we stop the recording here.